I'm here to talk to you today about biofabrication. I'm really passionate about this research area because it affords us the possibility of 3D printing body parts. This is especially important when you consider that millions of people every single year suffer a large amount of tissue loss as a result of genetic birth conditions, cancer, and also traumatic road accidents. I'm from QUT's Institute of Health and Biomedical Innovation, and this is over at the Kelvin Grove campus here in Brisbane. And here I work together with a wide range of health researchers, collectively working together to deliver real-world solutions to a range of health problems. I have a dynamic research team, and our vision is really to improve the health and well-being of the general population. And really our vision is to create customized tissue replacements to improve the quality of life for birth defect sufferers, cancer patients, and also traumatic accident sufferers. So let's just talk a few numbers for a moment. If we consider injury or damage to tissues and organs and put it into the context of congenital birth defects, we can see that millions of people every single year suffer from birth defects, such as cleft palate, where the roof of the mouth is not formed properly during fetal development. If you consider cancer, millions of people lose their lives every single day to cancer, and millions more are affected by this condition. And also, if we move on to traumatic accidents, many millions of people suffer road traffic accidents, skiing accidents, and really this leads to an awful lot of trauma to the body, skeletal, muscle, skin shattering into bits and pieces. So really, I'm driven by a need to try and ease the suffering for all of these people who suffer these conditions. So how can I reduce this suffering? Well, I do this by passionate collaborative research. We're developing new techniques and new technologies to afford us to be able to tackle all the aforementioned health problems. We're really developing custom replacement tissues and organs, and we want to be able to tailor these to the individual patient. And this might sound like science fiction to you, but really by working closely together, we're hoping to try to make this a future reality and to make this routine. So today I really want to talk to you about who we are and how we can get there. So I work with a wide range of scientists. We have a collective expertise and skill set. This includes chemists, biologists, physicists, mathematicians, engineers, and also medical doctors. And really, the spark of our vision, what really drives our research, is the desire to blow down those boundaries that separate these traditional research areas. We want to blow down those walls, bring all those researchers together to enable us all to work together and to meet these medical challenges. If you imagine traditionally a doctor would be working in a hospital, a physicist might be number crunching at their bench, and a biologist might be working with chemicals. If we try and bring all of this expertise together, we have a much better chance at combating these medical problems. So moving on to 3D printing and biofabrication. How is this a problem that we're tackling together? 3D printing is a rapid technique for creating a layer-by-layer structure. Here you can see a very simple plastic rocket being made. You can use 3D printing with almost any material, and you can do it on almost any scale. So here's a wonderful video that shows you, in China, they're basically 3D printing houses. So there's a concrete layer-by-layer structure where they're creating these three-dimensional environments. So the technology is really revolutionizing almost every industry in the world at the moment. These houses cost less than $5,000 each, and at the moment they can print up to 10 per day. I just thought it was a really wonderful video to show you this. And we also heard earlier on today that people are 3D printing little gadgets for iPhones to enable them to clip on cameras to scan the retina. So 3D printing is really being used all over the world at the moment. 3D printing is also fashionable. So I wanted to show you this slide because it just shows you how beautiful the outfits, the shoes, the accessories are, the level of detail that you can create with this technology. And here's just a little video to show you that on the catwalks of Paris, these clothes have been printed, and they're being modeled, and they're probably being sold for exorbitant prices. But it really gives you an idea of the level of detail of these clothings, the topography, just how much you can customize them to fit certain shapes of the human body. So you can imagine that if you can create these clothes that fit the outside of the body, it's not that complicated to be able to make them to fit the internal architecture of the body. So here's an example of a rather precarious pair of 3D printed shoes. Not really very surprising there. So let's just imagine for a moment that this model is unconscious on the runway. What happens next? So usually the next step is we admit them to hospital. They may have a really traumatic head injury, for example, and we have to have them undertaking medical scanning. Now, just to step back, this could be a model who's fallen off her shoes on the catwalk. It could also be someone who's had a road traffic accident or fallen over on the basketball court or on the ski slopes. So the first thing that happens is we take them to hospital and we give them a medical scan. So many of you have probably had CT scans, MRI scans. You're probably familiar with this kind of technique. So we can take a scan of the entire body and we can really start to look at where the defected tissue is and what kind of scale that's on and how we can deal with that. We next create 3D models of the injury. So we effectively create a 3D map of that defected tissue. We can look at the internal architecture of the tissue that's missing, and we effectively make this beautiful 3D model that shows us what tissue is missing and what kind of tissue we need to create to put back into the patient. The next step is we take this 3D model and we feed it into our computer programs, and they can talk to our 3D printers. We can program them to enable them to create a layer-by-layer approach to make a new scaffold. It's an anatomically precise scaffold. It exactly matches the medical data set. And we have these ultra-thin fiber networks. So a layer-by-layer approach to make a three-dimensional construct. And here's one I made earlier. I'm going to pass it around. Can I give that to you? Feel free to pull the scaffold out of the skull. So just talking very briefly about what kind of materials we use, because obviously we're not printing this out of concrete. We're not printing it out of that orange plastic that you saw the rocket was being made from. So we have to use biocompatible materials. That means they've been FDA approved to be implanted in the human body. We also make them dissolvable. So many of you might have had a metallic implant, and this causes problems in the airports when you go through the metal detectors, and it can also cause problems when you have to go back into the hospital to have another scan. So we're really thinking the future of regenerative medicine is to use dissolvable polymers. You implant them into the body, they slowly dissolve over time, the tissue grows back into the scaffold, it dissolves a little bit more, new tissue grows in, and you end up with a three-dimensional structure that just contains the tissue. The scaffold disappears completely. So we can tailor the dissolvability of these scaffolds, and we can also tailor the mechanical properties using polymer chemistry. So the next step, we need to add something else to that polymer to make it really heal the tissue in the body. So we use Bioinks. So Bioinks can encompass stem cells, any cells from the patient that you're trying to treat. They can also include growth factors that stimulate a certain type of tissue to be formed, depending on if you're looking at bone or cartilage or blood vessels, for example. Excuse me. So we've got a layer-by-layer approach with our scaffold and our Bioinks being printed into this 3D structure. So let's just zoom into that for a moment, just to check out what we've got in there. Please take notice of the little scale bar. So each of these fibers of the scaffold is half the size of a human hair. So it's really on a very small scale, which means it's emulating the tissue that's actually present in your body. And these little yellow things here are the cells. So these cells are residing within the scaffold. They're laying down new bone matrix, for example, or cartilage matrix within that 3D printed scaffold structure. They grow, they multiply, they lay down new tissue, that scaffold dissolves, the tissue grows some more, and you can start to see that those cells and that tissue is taking over that three-dimensional environment. But before that happens, we've printed our scaffold and our cells. We have to first of all implant that back into the patient. So the completed construct is implanted back into the skull. So let's have a look for a moment at some real data. So this is an example of one of our samples that we had implanted, and we wanted to see what kind of cells were present in there and how much bone was being formed. So this really shows you that you've got real bone tissue formed inside the scaffold. I'm not going to go into too much detail with the science here, but there's beautiful cell structures you can see there, are mature bone cells, and they're embedded in this beautiful mineralized bone matrix that exactly emulates what's present in your skin, in your bone, sorry. So we've got these osteocytes, which are mature bone cells, mineralized tissue, and the cells are talking to each other. They look like they're holding hands. They're talking to one another. They're saying, this is a great environment to be in. Let's create more bone. Very quickly, I'm going to go through some preclinical studies. There's a little bit of blood in these pictures, not very much, but if you're squeamish, then do look away. We've designed some 3D scaffolds, and we've cultured those with some stem cells, and we've also implanted those into a preclinical model. But very quickly, I just want to show you how we assess these scaffolds. So we use a process called histology. Histology is the study of human tissue, also other species of animal, etc. tissue. We take thin slices of the tissue like this, And we can then get a slice all the way through our scaffold, our 3D printed scaffold that's been implanted into our model, and we can look at just what kind of bone, cartilage, blood vessels has been formed within that scaffold. So here you can see all of this black area here. This is new bone. I'm not going to go into too much detail on that. If you zoom in a little bit more, you can see you have these sort of circular holes here. This is where the scaffold is still in place. The scaffolds in this case took about 3 years to degrade. So you've implanted them, they're slowly degrading. You can see the tissue around the outside of the scaffold is in blue. And if we zoom in some more, you can see all the new bone cells laying down new bone matrix. The black area is completely regenerated bone, and the blue area is new bone that's been mineralized around the scaffolds. So let's zoom in a little bit more. Because I love histology, I'm a histologist. This is an example of an area of the scaffold, the 3D printed scaffold that's been implanted. And here we've got a beautiful blood vessel going all the way through the scaffold. So we know that it's a physiologically relevant tissue. We've got these blood vessels that are feeding all the cells through the bone structure. And the cells orientate themselves around these blood vessels because they need to get nutrients and they need to flush out all of their waste products. So they orientate around the blood vessels, and this is a good indicator that our bone that we're forming in our scaffolds is physiologically relevant. So just very quickly, you can see with these, if you look at the white image here, this area here, right in the center, there's a blood vessel. So this is a textbook example of what bone should look like. You have a central blood vessel, and around that you've got your cells all oriented. So you can see that that really is reflected in the electron microscope image at the top. Blood vessel, cells, the same thing here, and the same thing here. So it's really important to demonstrate that what you're trying to create in the laboratory actually is physiologically relevant. So just very quickly, we also make different shapes of implants. So a tibial defect is a long cylindrical bone. So we make long cylindrical scaffolds to implant in there. Here's an example of quite a large 3 centimeter defect. We implanted a cylindrical scaffold into this defect here, which you can see here in the X-ray. And then we used CT scanning, which is to look at the mineral tissue inside that 3 centimeter defect, and also histology again. And you can see that in this case, with the empty defect where there's no scaffold being added, none of the bone's regenerated. In the bottom pictures, it's red. That means it's soft tissue. The black area is the mineralized bone, like I showed you before. So there's no bone healing in this case. If you move all the way to the right-hand side panel, you can see you've got beautiful black tissue forming all the way through that defect site. This means that our scaffold, with a growth factor called bone morphogenic protein, which I won't go into detail on, suffice to say that it's a growth factor that is used in the clinic to stimulate bone healing. If we 3D print our scaffolds, add these growth factors, we heal this defect beautifully. It's just very important as a scientist to point out this group here as well. So this is an autograft. Every single person in this room, if you suffer a small bone fracture, the first thing that usually happens when you go into the theatre is the doctor will probably take a chunk of bone from your pelvis and put it into that defect site. And that heals it beautifully. But then when you walk out of hospital, you're limping on this leg and you're limping on this leg as well. So it's not really an ideal treatment. And if that defect is very, very large, you cannot take enough bone from your pelvis to treat it. So 3D printing really affords us the ability to be able to make large scaffolds, customized scaffolds, very large, just in case the patient doesn't have enough bone available for bone transport. Okay. Last of all, I just want to very quickly mention that it's really important to be able to use these scaffolds to implant them and to regenerate bone and cartilage, but it's also really important to move with the times and to develop new technologies in the laboratory. So my groups currently, along with a lot of other groups here at QUT, are actually building 3D printers. So this is really exciting, and this really is something that we've been working on for quite a few years, and we're making some really great progress. Here's a quick video of one of our 3D printers. The quality is not incredibly good because the fibers are so very small, but you'll be able to see them shortly being laid down in a layer-by-layer approach. If you can just see the fibers there. So it really looks like a human hair, and we can build up these 3-dimensional structures that really look exactly like your bone tissue or potentially your skin or your cartilage. Okay, so what is the future of this technology? What is sort of my dream for how this is going to be applied to improve human health and well-being? Well, my vision is a hospital of the future. So ultimately, when a patient is admitted to hospital, we would hope that if they had a head injury, for example, next to their scanning equipment, there would be a 3D printer in all hospitals. They can make customized, sterile, on-the-spot implants. It could heal bone or cartilage or blood vessels, multiple tissues and organs, and immediately be implanted back into the patient, and they will get discharged much faster, and they're renovated back to their beautiful self. So just to reiterate, 3D printing, we hope that that's eventually going to be able to make customized, anatomically precise tissue replacements for patients who may be suffering congenital birth defects such as cleft palate, people who've had tumor excisions as a result of cancer treatment, for example, a breast mastectomy, or also people who may have suffered very, very traumatic accidents. They've shattered their femur, they've shattered their tibia, they've lost a great deal of tissue. We hope to be able to make 3D customized tissue replacements, and hopefully these will be present in all of the hospitals in the world. And we think this is one of the future strategies of regenerative medicine. Just very quickly, I want to acknowledge all of the amazing people who contributed to this work. I'm here today just representing a team of wonderful scientists. So this is the Biomaterials and Tissue Morphology group at QUT, who really work very hard in the laboratories to build this equipment, to create these scaffolds, to implant them, and also to look at how the bone is healing. And last of all, I'd really just like to say thank you to the TEDx organizing committee, to our wonderful compere, to all of the students who enabled us to be here today. I've had a really fantastic day. It's been amazing to see all of the talks, and really it wouldn't have been possible without all of the TEDx organizers. So thank you very much. And thank you for listening, and thank you to you guys at the block, at the cube, sorry.